Hello everyone, my name is Yiran. This is the third presentation for CS 520. I'm on topic 3, which is to prove the sum of k cubed for k is 1 to n, and this entire summation equals 1/4 times n squared times n plus 1 squared. Let's first begin with the definition. A proof by induction is just like an ordinary proof in which every step must be justified. However, it employs a neat trick which allows you to prove a statement about an arbitrary number n by first proving it is true when n is 1, and then assuming it is true for n is k, and then show it is true for n is k plus 1. So let's start with our case today. I put it here so that we can easily look at it when we're doing our proof. The first step is the base case, which means n is 1. So we plug in n is 1 for both sides of the equation. On the left-hand side, we get the sum of k cubed for k is 1 to 1, which is 1 cubed, and it is still 1 in the end. On the right-hand side, we get 1/4 times n squared times n plus 1 squared. We plug in 1 for n, so we get 1/4 times 1 squared times 1 plus 1 squared. The 1 plus 1 squared is 2 squared, which is 4. So here we have 4 times 1 times 1, and we have the 4 in the numerator. And we divide it by 4, so we get 1. And in the end, on the left-hand side, we get 1. On the right-hand side, we get 1. So the base case is proved. So let's turn to the inductive hypothesis. In this case, we have to let the n to be L plus 1. So on the left-hand side, we'll have this new summation. What I want to do is to split this new summation into two parts. If we want to split it, we have to take the very last number of the summation, which is L plus 1. Because we have the k cubed here, if we want to take the L plus 1 out, we have to multiply the L plus 1 3 times. So what we get here is the L plus 1 cubed plus our new summation, which is the k cubed for k is 1 to L. It is hard for us to continue if we have the summation here. So what we can do is refer to this equation here. We can see that this summation has exactly the same format as this summation here. So we will express this summation in this regular form. The only thing we need to do is to switch the n here to be the L, and it is what we have here. If we multiply the L plus 1 twice, it is easy for us to get this expression. And I put the 4/4 here just for our later reference. And for here, I multiply this 3 terms by the L squared here, and this is what we get. So now I rewrite this L plus 1 cubed in this form, and from here I get the L plus 1 squared into this form, and I directly move this L plus 1 here, and this is how I get this step from here. And then I multiply these two terms and I get this entire thing here. So now what I did next is to drag the 4 into the parentheses. So each term in the parentheses has to be multiplied by 4. And this is how I get this step. What I'm doing right now is to factor out this 1/4 and this 1/4, and then add all the items in these two parentheses together, and this is what I get in the end. We also need to plug in L plus 1 for n in the right hand side but the only thing we need in this situation is calculations. If we plug in L plus 1 for n, we get 1/4 times L plus 1 squared times L plus 1 squared. And L plus 1 equals L plus 2. So if we multiply the L plus 1 twice and L plus 2 twice, and this is what we get. So from here, I multiply the L squared plus 2L plus 1 by the L squared plus 4L plus 4. And this is the expression that I get. And if I simplify it, this is the expression that I get for the right-hand side. So remember the expression here and look at the expression here. And we found that we get the same expression. So the inductive case is proved, and hence the entire case is also proved. Here's my reference page. Thank you for watching and have a nice day.